All right, so unit exam review here for Unit 4. This unit had two kind of distinct parts to it. It had the first part, which was about simple harmonic motion, and then the second part, which was about waves. Okay, and of course we learned right away that waves are the result of simple harmonic motion, okay, which is why the two things go in the same unit, but it does kind of make a unit with two distinct halves. Okay? So first thing we talked about was simple harmonic motion. In terms of the bulk of the assessment for that, a lot of it is terminology, and thus will be in the multiple choice. When we're talking about what are the conditions necessary for simple harmonic motion, types, things like that, your mass on a spring, your pendulum, what are the things that affect the period of those, that kind of stuff could all be in the multiple choice. Okay, so we'd be looking at like the nature of it. Okay, and by nature, I would say one of the most important things would be this. Restoring force must what? Vary linearly with displacement. Essentially, Hooke's law, which would also be part of simple harmonic motion. Okay, that would be the important thing. Okay, know the two examples. Okay, pendulum. Length and gravity. Okay, and mass on spring. Okay, mass and spring constant. Okay, those would be the things that I would say are going to be a big part of just your understanding of simple harmonic motion. In the written response, I would expect probably one problem related to either one of those, okay? Or maybe even a simple multiple choice calculation where you're doing something with the period of either one of those, okay? And then as part of simple harmonic motion, we talked about Hooke's law. Okay, there might be the odd multiple choice question about Hooke's law, as long as we understand that it's basically about the nature of simple harmonic motion and that the restoring force in an elastic object is negative k times x. Okay, I'd say that's the bulk of it. I will test it in the written response with a problem. Okay, now the most common place we talked about Hooke's law being used in a problem was if we were calculating maybe like acceleration, okay, or if we were putting, two kind of situations together where maybe it was, like what Hooke did in his experiment where he had masses hanging from the ceiling so that the force in the spring was equal to what force? Gravity. Okay, situations like that. Whenever it's a Hooke's law question, it's going to be Hooke's law is equal to m times a, or m times g, or something like that. That's the whole point kind of Hooke's law, is that it is the net force in a situation involving simple harmonic motion. So if you understand that part, you're good for the multiple choice. You can solve a problem like that, okay, where the force in the spring, okay, is equal to F net, which could also mean the force in the spring is equal to gravity if it's a hanging spring. Okay, those are the situations we dealt with in class. I'm not going to surprise you with some outside the box situation you've never dealt with. Okay. So expect a little bit in the multiple choice. There's not much multiple choice. What is it? 15. Geez, I've made so many tests in the last little while, so I'll learn to get it. I'll go over it with you, but it's like 14 or 15. It's not much. Okay, and then obviously a problem-solving thing related to. What's the negative for? Right, it makes sure that the force is always opposite the displacement. So if I stretch a spring to the right, the forces are going to pull to the left. Simple as that. Okay, from Hooke's law, we went to conservation of energy. But before we went to conservation of energy, I talked about how Hooke's law relates to elastic potential energy. That's this. And I referred back to your lab from Science 10 about the rubber band and the work done in stretching it. Okay? And we talked about how elastic potential energy has to do with using spring force and multiplying it by distance. Okay? Basically it was, if you apply a force to an elastic object, you'll get a graph that looks like this. Okay? And the energy or work done in the spring is going to be equal to 1/2 of that maximum force multiplied by the distance. In other words, the area underneath the line, which would be 1/2 kx squared, or 1/2 k times x times x. Okay? And that's where that formula comes from. There is probably a need for you to understand that for a multiple choice question. Okay? Then we talked about conservation of energy in two different situations. The pendulum was not new to us. We already had talked about pendulums back in Unit 2, and a pendulum uses gravitational potential energy, so setting up a conservation of energy problem with a pendulum is just like doing a roller coaster question, or a kid sliding down a hill question, or a person riding a bomb out of a plane question, okay, or whichever situation we have. It's gravitational potential energy, okay? So yes, it's EI equals EF, but it's m times g times h initial plus 1/2 mv initial squared equals 1/2 mv final plus mgh final. Okay, it uses gravitational potential energy. Now, the other things we have to remember for both a pendulum and a mass on a spring, lazy, I'm going to abbreviate, okay, is that they both set up like this, EI equals EF. It's law of conservation of energy. That part doesn't change. Okay, but that for this one, it's going to be that elastic potential energy, so 1/2 kx squared initial plus 1/2 mv initial squared equals 1/2 kx final squared plus 1/2 mv final squared. Now, for both of these, we have to remember that there's a maximum amplitude and an equilibrium position. Okay, so if we're talking about a pendulum, right, it could be here at equilibrium, it could be here at its maximum amplitude, or here at its maximum amplitude. Okay, and then it's going to obviously swing through that arc back and forth, back and forth. Okay, when it's at its maximum amplitude, it only has potential energy, because at this point it has stopped for an instant. Okay, so here would be potential energy maximum, or only, and at equilibrium, only kinetic. It can't fall any further than that. Okay, it would be at its maximum speed and have no potential energy at that point. Okay, because there's no restoring force present at the equilibrium position. Okay, and the same is true for our mass on a spring. So at the point of maximum compression, we only have potential energy. In fact, we said that we don't use x, we use a for the maximum amplitude. Okay? Okay, here at the equilibrium position, we would only have kinetic energy because there's no displacement, x is 0, and if x is 0, there's no restoring force, and thus there's no potential energy there. Okay? And this would be EK maximum, and then out here, wow, my mask got differently shaped there. Sorry about that. Okay, it's back to our maximum potential energy. There's maximum potential energy for both of these examples at their maximum amplitude on either side of equilibrium. Okay, so definitely expect a law of conservation of energy question on your test. Okay, and I didn't make it the hardest possible. In other words, it's not going to be like 1/2 kxi plus 1/2 mvi, and there'll be a value for both. Okay, and then the same thing on the other side, but that's going to be a value for x and a value for f. We didn't do very many like that in class. We mostly dealt with maximum amplitude and equilibrium. So expect I'm not going to go much beyond that on your test in terms of level of difficulty for that type of question. Okay, the trick here is that Hooke's law questions, law of conservation of energy questions related to masses on springs give a lot of the same information. So it's important to be able to tell them apart. Okay? A law of conservation of energy question will always give you information about 2 points in the oscillation, so you can compare them. A Hooke's law question will only ask you about 1. Okay? And it would generally ask for things like displacement or acceleration or spring constant. Or maybe mass if it was like a hanging object. Okay, something like that. All right. Questions on that part? Then we went to properties of waves. That was the last of the conservation of energy stuff. Okay. So the stuff you did on your assignment for simple harmonic motion, you guys did well on that. Don't expect that I'm going to ask anything harder than what was on that. Okay. In fact, probably most of the stuff is easier than what was on there. Okay. Properties of waves. So all of lesson 9 basically is tested in the multiple choice. Okay, because there's not a lot of calculating when we're talking about the properties of waves. A wave is a traveling disturbance. It needs a medium in which to propagate. It has the following properties: amplitude, wavelength, period, frequency, speed, okay, all of that kind of stuff. That's all multiple choice. In fact, the bulk of the multiple choice is actually about waves, okay, more so than it is about simple harmonic motion. So yeah, just know the properties of waves. Go over lesson 9. There's no problem solving to do with that. You just need to know terminology. Okay. For universal wave equation, obviously we use that in everything for the second half of the unit. Okay, we use it for on its own. We use it for standing waves. We use it for air columns. Could even possibly get worked into a Doppler question, but I'm not that sadistic, so I didn't. But it's certainly all of that stuff could be in. Okay, it's something we use all the time. That's why it's universal. So expect that I will have a question that is just about wave properties and the universal wave equation. Okay, the examples we talked about in class were the tricks, right? Like if 8 crests go by, it's only 7 waves. Okay, or echo questions were another way that we did universal wave equation. There were really only those 2 types. So spoiler alert, expect one or the other on your test as just a simple universal wave equation problem. But I would make it 2 parts. Okay, so there'd be some stuff about wave behavior and some stuff about universal wave equation kind of in the same question. All right, we talked about interference, and I told you the day we did interference that these questions are going to be mostly diagrammatic. But there's also a 2-speaker question. Okay, and I told you that the day we did it. And so there'll definitely be a 2-speaker question about interference, whether the person hears a loud sound or a quiet sound. But there's also a diagrammatic question worth 3 marks, where I put 2 overlapping waveforms on and ask you to draw the resulting waveform. So if I gave you wave A, let's pretend I drew that better, and wave B, and said, what kind of interference is this? Draw the resulting waveform. 3 marks. Okay, so what kind of interference is this? Constructive, they're in phase. Okay, the resulting waveform would be, now I would have this on graph paper. Okay, like I superimposed it onto a grid so that you can actually calculate how tall the resulting wave should be. Okay, that's what you're going to get your 3 marks for. 1 mark for constructive, 1. Done. Okay, so it's either going to be constructive or destructive. Okay, you just have to draw it. Okay, waves at a boundary. There's some multiple choice with diagrams. Like I said, the bulk of the multiple choice is about waves. Okay, there's lots of diagrams of waves. So this is when a wave goes from a slow medium to a fast medium. What happens to it? Well, some of it's transmitted, some of it's reflected. What does the reflection look like? How can I tell it went into a slower medium or a faster medium based on the structure of the wave, or what the reflection looks like? Those kinds of things. Multiple choice questions with pictures is how that's going to be assessed. There's really no way for me to ask about that in a written response question. Okay, so that's going to be multiple choice, right? So if I had, let's say, that being the before picture. That being the after picture, I might ask something like, did this wave enter a more dense or less dense medium? Less dense, okay? Two ways for me to know that. The transmitted wave is longer, thus traveling faster, and the reflected wave is upright, went into a less dense medium. Okay, that would be a multiple choice question. Okay, and those ones should be pretty easy because it's the end, like it's really only two possible answers, right? More dense, less dense. I gotta make up two other things in there that are gonna be obviously not right, like impossible to tell and, you know, I don't know, something else maybe. Okay, so there's really only two possible answers. Okay, you just gotta get it right. All right, standing waves. Okay, terminology is important. Nodes, antinodes. Okay, being able to calculate the wavelength. Okay, if I show you a picture, so if I say what's the wavelength? 2 meters. Okay, there's two wavelengths on that 4-meter stretch. Okay, so stuff like that, just being able to recognize. Okay, or what's that called? A node. Okay, what's this called? An antinode. Stuff like that. Okay, just know your terminology because those are the terms I'll use in a written response question as well, so you have to know them. Okay, but in terms of standing waves, mostly the problem solving is going to have to do with air columns. Okay, and I will tell you the question has a part A and a part B. Okay, so like one part's kind of like what your quizzes were this morning. The quiz questions this morning are very much like the question I put on the test. But then a part B might ask something like, what's the next frequency that you might hear? Okay, and that could be different depending on whether it's an open air column or a closed air column. Okay, so that would be kind of the part B part. Now, if I know what F1 is, okay, what would F2 be? 2 times F1. So things like that. Okay, you have to know that and be able to apply it to a question. Right? There's nothing really going to be a surprise there. Okay. Any other questions on that one? And Doppler effect is the last thing. So we went over that kind of stuff yesterday. You guys didn't seem to have too much trouble with the problem solving. There's a Doppler effect question. And it's very much like the last example we did yesterday where I gave you the air temperature. Okay, and then you have to calculate one of three things. The Doppler frequency, the original frequency, or the speed of the train. It's a train. A Doppler effect question is about a train. Okay. Yeah, so one of those three things, okay, is what you have to do for the Doppler effect question. Okay, that's what's on there. Let me give you a bit more detail here. Okay, so, okay, 14 multiple choice. Okay, 14 multiple choice, and there are 9 written response questions. Okay. And in the multiple choice, like I said, there's a couple of questions about simple. There's 3 questions about simple harmonic motion, and the rest is waves. 11 questions in the multiple choice on waves, 3 on simple harmonic motion. And there's, like I said, lots of diagrams, stuff about, you know, like I said, about wave properties. What property of a wave would we associate with pitch or volume or, you know, things like that. In the wave behavior, the boundary stuff, okay? One about wave motion and the motion of the medium. So a wave is going through, what's the medium doing? There's a question about that. Okay, diagram related question about what is the medium doing when this part of the wave is approaching? What's the medium doing when this part of the wave is approaching? Okay, you know, it's still simple harmonic motion. There's points where it's trying to go back to equilibrium. There's points where it's trying to go away from equilibrium. Okay, it's a diagram question about that. What property of waves never changes? Okay, that might be in it. Yeah, and then some diagram questions. And the last 4 questions are about the wave behaviors we went over. Reflection, refraction, interference, and diffraction. Okay? There's the last 4 questions are diagrams about that, being able to recognize that. Okay? In this picture, which one's going on? In this picture, which one's going on? In this picture, which one's going on? And I will admit that they are very crudely drawn pictures. Because I do. Okay, in the written response, okay, we got the wave, the interference question, we got the air column question, and we've got the universal wave equation question that actually, sorry, I forgot I changed this one. It's actually 3 parts. None of them are difficult. It's 3 parts. Then there is a simple harmonic motion problem. And then another simple harmonic motion problem to do with energy. And then a simple harmonic motion problem. And then a Hooke's law question. A Doppler question. And a 2-speaker question. Okay. So like I say, some of these will go fast because it's basically just drawing something. 9 questions, I get it sounds like a lot. It's the most we've had on a test for written response, but these are also some of the shortest written response you've ever had as well. Like, you've never had a question where you just had to draw a picture. Okay. And the written response, that one's going to take you like 15 seconds to do. Yeah, and then some of the other ones are pretty quick written response questions. So 14 marks in the multiple choice, 47 marks in the written, okay, for a total of 61, which makes it only a little tiny bit more than your circles test, which I think was 58. Okay, so it's on the shorter side. Your kinematics was like 80 something. That's a lot. All right, questions from you guys? Want some practice questions? I made a few up. Okay. That might be on there. Try that one. Okay, so we've got 2 speakers that are 2.815 meters apart because, well, that was the distance they needed to be for the numbers to work out. Okay, 2.815 meters, and are emitting tones of 523 hertz. Okay, an observer is directly in front of one speaker and is 1.625 meters away from it. And their arms come right out of their neck, I guess. That's the way I drew them. Okay, so this is 1.625 meters. Okay, that's our 2.815. So that would be how we would start this. We would obviously need to know this distance here, which we'll just calculate using Pythagorean theorem. Alright, so we'll have the square root of 2.185 squared plus 1.625 squared. Whoop. Alright, so 2.723, we'll keep all those decimals. Okay, but for now we'll just write that. What's the next thing I've got to calculate?
I think you calculated the side of the triangle wrong.
2.8.
I was going to say, why is that shorter than that? The last time I checked, the hypotenuse is the longest. So. Can I start over? No? Okay, well fine, I'll just do with the wrong numbers. Alright, second entry. 8. Better, 3.25. Okay. Alright, so now we've got that. What do I need to calculate next now that I have that right? The wavelength. Okay. So wavelength, sorry, we also have the speed, 340 meters per second. I forgot to write that down. So wavelength will be V over F, 340 divided by 523. Okay, so we've got 0.650 as our wavelength. All right, what do we do next? Right, calculate the number of wavelengths between the speaker and the observer in both situations. So to do that, I take the distance, I divide it by the wavelength, okay? Whoop, 0.650. Okay, so 1.625 divided by that number. Okay, gives me 2.499. Can I say that's 2.5? That's close enough to 2.5. Okay, and I got to do the same thing here. So 3.250. So I'll take that number. So I'm using all the decimals and divide it by that number. Is that close enough to 5? Okay. Okay, loud or quiet? Quiet, okay? When I subtract these two, I go 5 minus 2.5, I get 2.5 wavelengths difference. That means they arrive out of phase. One arrives as a crest, one arrives as a trough, and they interfere destructively, and I hear a quiet sound. Okay, everybody all right with that one?
Why don't you hear no sound?
Well, because unless you're in an anechoic chamber, there's always going to be some reflections off the walls and stuff like that, so you're going to hear something, right? Unless you're in a acoustically perfect anechoic chamber where you would hear nothing. It's just not realistic to have that situation. I mean, if you wrote nothing, I could still technically say, well, you knew it was destructive, and I wouldn't mark that wrong, but I mean, loud or quiet, it's one or the other. Okay? Different kind of question? Okay, give that one a try. Okay, so what kind of question is it? It's a Doppler effect question, okay? And we can recognize that because they're talking about different frequencies and they're giving you two different ones. They're talking about what an observer hears, okay? And so definitely a Doppler effect question. So we know the speed of the source is 180 meters per second, and it's moving towards the observer, so we're going to be subtracting Vs in this situation. Okay. The observer hears a sound, so that's the Doppler shifted frequency of 925 hertz. Okay. And we know that the temperature of the air is 32 degrees Celsius. We are looking for the actual frequency of the engines of the plane. First thing we have to do is calculate the speed of sound using this formula. Okay, times 32. Okay, so we're looking at 351.2 meters per second. Okay, now that we have that, we can look at this formula, F equals FO, which is what we're looking for, multiplied by V over V minus Vs because it's an approaching source. Okay, so to manipulate, all I do is bring all the brackets over to the other side, so we'll have this equals FO, plugging in my numbers, 925 over 351.2, over 351.2 minus 180. Okay, will give me my original frequency, so 925 divided by, in brackets, 351.2 divided by, in brackets, 351.2 minus 180, bracket, bracket. Okay, so the actual frequency of the engines is 451. Actually, we only have two significant digits, so 4.5 times 10 to the 2 hertz. Okay, everybody all right with that one? Okay. Want another? Give this one a try. Person in their boat. So for this one, I would say the big thing is draw a picture so you get the wavelength right. Okay, they're 30 meters away from each other, but when one is in a trough, the other is on a crest, and there's 3 crests between them. So I'm going to start out with the guy in the trough. Okay, so this is the boat that's in the trough. Okay, and then there's going to be 1, 2, 3 crests between them. Okay, so there's the other boat.
The waves are slightly over.
What?
Like if you take like even just like a second later, then they're before in between them.
But we're not talking
But then-
about a second later.
But a second later, he would be here and he would be here. They would still be the same number of wavelengths apart.
Yeah, but there's 4 crests between the boats.
No, there's 3 crests between the boats.
If
He's
you
on
take
top
it a
of the
second
boat.
later, then there'd be 4 crests between the boats.
But there'd still be the same number of wavelengths.
Yes,
between
there
the
would
boats.
be.
Okay, but this is the only way you can get the wavelength. If I say he's 2 centimeters down the crest on the other side, it's a little tougher.
Never mind. Because it doesn't specify 3 crests between the boats when the
When
boat
one
is-
boat is on a crest, the other is in a
But
trough.
the but is implying a different part of the sentence, not necessarily.
Oh, I actually get it. He's implying that it never actually specified that when a boat was on a crest, that the other is in a trough. He just said that they're a half wavelength apart. So if they were in between the wavelengths, like at equilibrium or whatever, then there's 4 crests in between them.
I think you guys are really overthinking it. I'll give you that, okay, you could possibly interpret it that way if you overthought it. I'm sorry, I'm not trying to gaslight you here, but it's like, don't overthink it, right? Here's the situation, draw the picture, it looks like this. Yeah, I get it. I wouldn't take it that far. I'd make it as simple as possible. I'm not trying to trick you, right? Yeah. Okay, so if we've got 30 meters, if this distance here, okay, is 30 meters, okay, we've got 1, 2, 3, 4 crests, which is how many wavelengths?
4.
3. And half. Okay, so there are 3.5 wavelengths in 30 meters. Right, so we divide our 30 by 3.5, and we'll get meters per wave, which is the wavelength. Okay. Okay, so our wavelength is 8.57 meters. Okay, we'll just leave that in there, and we'll just write 8.57 here. Okay, for the wavelength. Okay. so now we know the wavelength, and it also tells us that the period of the waves is 12 seconds. All right, I have lambda and I have t, and the other version of this is lambda over t. Okay, I could just calculate f and then go 1 over f, but this can do it in one step if I recognize it. Okay, and we'll have our 8.57 divided by 12. Okay, so our wavelength to 2 significant digits would be 0.71 meters. Okay, so at that instant in time, where they are in that exact orientation, and there are 3 crests between them, this would be the answer. Okay, and again, I'm not trying to make fun of you here. I'm just saying, like, you always consider it the simplest way. Okay, I'm always trying to make it the simplest way. I'm freezing a moment in time and saying, here's the position of the boats, and here's the number of crests between the boats at that same instant in time. I wouldn't be trying to make it more difficult by saying we're at an intermediate point, because I get it. There would be 4 crests between them an instant later. You're absolutely right about that. But they would still be the same number of wavelengths apart at that point. But it would be much harder to calculate the wavelength an instant later. You follow me there? Yeah, like if I say, oh, an instant later, this boat's right here and this boat's right here, now calculate the distance between them. Well, the number of wavelengths between them, they're still 30 meters apart. But now it's like, okay, how many wavelengths is that? It's much more, like, it's more estimation, which I don't think is a fair way to have you measure something, if that makes sense. Yeah. All right, any other questions on that one? Okay, you want another one? That's a simple one. But there might be one that's simple on the test. Okay, all right, so we've got, we're looking for the acceleration due to gravity. Okay, so we're looking for g. We know the length of the pendulum is 1.2 meters. We know the period of the pendulum is 2.5 seconds. Okay, so t equals 2 pi times the square root of L over g. Okay, we have to manipulate for g by squaring everything. T squared equals 4 pi squared times L divided by g, and then we just swap g and t. Okay, so we'll have g equals 4 pi squared times 1.2 divided by 2.5 squared. Okay, so 4 pi squared divided by 2.5. Whoops, I forgot to do the times L. Times 1.2. Now divide that by 2.5 squared. All right, so we are looking at an acceleration due to gravity of 7.6 meters per second squared. So obviously not Earth. Okay. Everybody all right with that one? Okay. Tired of doing my practice questions? I heard a yes. Anybody else want one? How many more do I have? Holy smoke, I was on a roll. Okay, all right, try the mass on the spring one. I couldn't remember how many I made. All right, a mass on a spring. We know the spring constant of the spring is 2.5 newtons per meter, is oscillating with simple harmonic motion. Most of the time, okay, if it's oscillating, it's not a Hooke's law question. Okay, unless it's asking, like, what's the acceleration of this particular point in the oscillation? Okay, in this case, it's asking how fast is it going. Do we ever solve for speed with Hooke's law? No. Okay, and that's, again, how you can tell the difference between a conservation of energy problem, this one, and a Hooke's law problem. All right, so the maximum amplitude, where it would only have potential energy, is 0.65 meters. Okay, the mass is 1.5 kilograms. Okay. And we know we're looking for how fast it's going when it is 0.22 meters from equilibrium. Okay, so we have xf. We're going to say the amplitude is the initial right, and set it up to solve for VF. So we'll say, yep, EI equals EF. Okay, our initial energy is going to be the maximum potential energy, and that's going to equal 1/2 kxf squared plus 1/2 mvf squared. And we can get rid of the halves right away because it's in every term. And then we simply need to isolate xf. So I'm going to bring the mvf squared over to this side by subtracting. So ka squared minus mvf squared equals kxf squared. Sorry if I put squared there. Dividing both sides by k. Okay, and then square rooting will give me my xf. So when I plug in my numbers, it looks like this. And I should get a final speed at that point of 0.79 meters per second.
It doesn't really matter, but up there you were isolating for X, not for V.
Oops. Man, I gotta sleep more. It's not with it. Yeah, you are absolutely right. Because I wasn't paying attention. Sorry. Do this. Ka squared minus mv squared equals k. I just did the same thing. My God. I need to go back to bed. There. No, it's all right. Sorry, guys. I'll be better tomorrow. Promise. When we're doing our lab activities, because you know it's a safety thing. All right. All right, we'll leave it at that. But obviously, you got your review sheet that you can use. Getting test Thursday. All right. You need some more help? Hop in. I'm here all week. Something like that.